All right. Well, hopefully everybody did a good job with and problems, independent and dependent events. So in this section, so we're not actually going to be doing probabilities in this section, but it's going to build us into the next section, which is going to be using these topics: fundamental counting principle, permutations and combinations, to actually find probabilities with them. So right now, everything that we're working on is just kind of focusing on what's called some kind of different counting techniques. So we won't actually have fractions in any of our answers. These are all going to be like whole number answers and stuff like that. So kind of keep that in mind. So I thought we'd start off right away with a little example here. So suppose you're choosing your class schedule and you need to take a math class and a history class. And so we've got some different choices for these guys. And so what we want to do is try to figure out, well, how many different schedules could I actually make with these, 5 different choices and 2 different classes. So I'm going to label these a little bit so I don't have to write as much stuff down. So I'm going to call math Monday, Wednesday, 8 o'clock, kind of A, this one B, this one C, and then I'll call this one D, and this one E for the history classes. And so what we're going to do is kind of like we did with that multiplication problem in the last section. We're going to make a tree diagram in this case. So what I'm going to do is I'm going to start off with the math classes first in my tree diagram. And so since there's 3 choices for the math classes, I'm going to draw 3 branches. And I'm going to label each one A, B, and C. So A, again, is the 8 o'clock. The B is the 9:30 to 10:45. And then the C is the 12:30 to 1:45. And now my second branch is going to be the history class. And since there's 2 of them, then what we want to do is make 2 branches off of each of these. And so again, D represents the Tuesday, Thursday, 8 o'clock. E represents the Tuesday, Thursday, 2 o'clock. And so if we go through and just kind of count the ends of the branches, that'll tell us how many possible ways we could schedule these 5 classes into just 2 class combinations in this case. So how many possible schedules are there? So it looks like there are 6. And so the nice thing is about the tree diagram, they take a long time sometimes to draw out, but at least you can kind of look and see what the schedule would look like. So in this case, this first branch would be like A and D. So that means I'd have the Monday, Wednesday, 8 o'clock math class paired with the Tuesday, Thursday, 8 o'clock history class. Or I could do, like, let me go down here. I could come down this way and go like CE, for example, which would be the Monday, Wednesday, 12:30 math class, or the 2:30 or 2 o'clock history class. So again, it allows you to go through and actually look at each of these different possibilities. All right, so let's throw a little twist in here. So now what if we say, okay, well, I actually really need to take 3 classes. And so I'm still going to use the same 2 from above. So I'm going to kind of keep those as A, B, C, D, and E. And then I'm going to add in these 2 science classes, which I'm going to call F and G. So again, I'm going to kind of start off the same way. So I'm going to do math as my first set of branches. And so again, I've got A, B, and C. And so for my second set of branches, it's going to be the history classes, which were ABC, so D and E. So I get D and E repeated a bunch of times off of each one of these. But now I want to add a science branch that contains F and G. And you almost always run out of room on these, no matter how much space you leave. So again, just like before, now that we've got all of our branches filled out, we go along the edge, count up how many total branches we have. So 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So we ended up with 12 in this case. So when we were picking 2 classes, we ended up with 6. And when we were picking 3 classes, we ended up with 12 possible schedules that we could have. So hopefully by kind of looking at these, we notice some sort of a pattern. So in this case, the math class had 3 choices for math, 2 choices for history, and lo and behold, our answer was just same thing as 3 times 2. And similarly, if we looked at 3 choices for math, 2 choices for history, 2 choices for science, we ended up with 12, which lo and behold is the same thing as 3 times 2 times 2. So what we've actually done here is kind of discover what's called the fundamental counting principle. So the fundamental counting principle is just pretty much a way to count things that are broken up into different categories. So if I've got, like in our case, like math was a category, history was a category, science was a category, and we just take these categories together, and instead of having to draw a tree diagram every single time, we can just multiply each of these different categories together and get our actual answer. And so in short terms, that's kind of what everything in that green box is saying. So with that in mind, go ahead, pause the video at this point, work on practice 1 and practice 2. And so in this case, we've got, I've kind of labeled the categories for you just so you can kind of see them out. And then practice 3, same kind of idea. Like the categories would be the number of bedrooms, the number of bathrooms, whether it's first floor or second floor, whether it has a lake view, golf course view, or no special view. And then try to figure out how many apartments there are. So this one, 4 and 5, I'm curious to see how you do. This one's might be a little tricky for you, so I'm not going to give you any hints at the moment, but if you get stuck on it, message me, and then I'll throw some hints up on the board to kind of help you out with those. So at this point, pause the video, and then come back in a bit, and we'll talk about permutations. All right, good job, good job. So at the moment, I'm not going to talk about what a permutation is, but the cool thing is permutations and fundamental counting principles are very similar. So in this case, I'm going to say I'm in charge of the FCC movie marathon. I have 4 choices for movies: action, comedy, drama, and horror. And since I know the fundamental counting principle, it's asking me how many different ways are there to order these 4 movies. So the way I like to do these problems is I kind of like to imagine like a box, or you can draw a line, whatever you want to do, kind of representing each movie position. So for example, let's say we started the first movie at 6 o'clock. So like this would be like the 6 o'clock time slot. This would be like the 8 o'clock time slot, the 10 o'clock time slot, and then finally like the midnight time slot. So in this case, when I look, I've got 4 possible movies, I've got 4 positions. So how many choices do I have for the first movie in this case? So, well, any of them. I could play action first, then comedy, then drama, and horror. And so now, for the second movie, I probably wouldn't, if I played the action first, if I played the action again, more than likely everybody would leave because they probably wanted to see something different. So the idea is I need to play something different, so I'm eliminating that thing from the list. And so that's kind of the difference between a permutation and a fundamental counting. Fundamental counting, you never really get rid of anything. There's always the same number of objects. Permutations, if you use something, you get rid of it and it reduces the number. So in this case, if I played action first, then that means there's only 3 possible choices for that 8 o'clock time slot. And then if I played, say, the comedy next, now there's only 2 possible choices. And then finally, 1 possible choice. And so now I just multiply these together just like fundamental counting. So 4 times 3 is 12, times 2 is 24. So it turns out there's 24 ways that I can actually play these 4 movies in different orders. All right. So again, what I just said, this is what's called a permutation. So again, it looks similar to a fundamental counting principle, and the concept's pretty much the same. The only difference between permutation and fundamental counting principle is that items are not to be used more than once in a permutation. So I highlighted that down here. No item is used more than once. In a fundamental counting, items can be reused. You can reuse the item more than once. Permutation, we cannot reuse the item, and the order matters. So in this case, notice the 4-3-2, like it would be a big difference if I played the horror movie first, then I played the action movie first. So order of these do matter. So again, that's something to keep in mind. All right, so let's continue on with our movie marathon. And so in this case, since we know people sometimes don't like horror movies, we decided it should be the very last movie that we play. So with this in mind, how many different ways are there to arrange those other 3 movies? So again, I'm going to do it the same way. I'm going to kind of lay out my different time slots. There's 6 o'clock, 8 o'clock, 10 o'clock, midnight. But in this case, since I've decided the horror movie's going last, I'm just going to go ahead and stick it in there. And so that choice has already been made. So now if I go back to the 6 o'clock time slot, there's the action, there's the comedy, there's the drama. So I've only got 3 possible choices for what movie could go first. And then similarly, I'm not allowed to repeat any movie. So I've got 2 choices, then 1 choice. And then we don't multiply the H, that's just there. So just 3 times 2 times 1 gives us 6 choices, with the horror movie as the last possible movie. All right. Is that okay? All right. So again, example 5, kind of continuing under this same movie marathon idea. So in this case, though, what we're doing is maybe all of a sudden FCC decided, oh, well, you can't be here until 2 o'clock in the morning playing these movies. You got to be out of here by 10 o'clock. So we only have time for 2 of the 4 movies in this case. So the only difference is, since I'm only picking 2, then that means I'm just going to draw 2 boxes. So it doesn't affect how many movies we have to choose or anything like that. It just limits how many time slots we have. So in this case, I'll put like the 6 o'clock time slot and the 8 o'clock time slot, and then we have to be off campus. And so in this case, there's no restrictions. So if we want to play the horror movie first, we can. So that means we've got 4 possible choices for the first movie, 3 possible choices for the second movie. And so in this case, that gave us 12 choices of how to play 2 out of those 4 movies in this case. All right, is everybody okay with that? All right, perfect. Very good. And so in blue here, so I've kind of gone through and explained. So there is a formula for permutations. And so it's a little bit complicated to look at. And so it involves explanation points and things like that, which you may not have even known of in math. And so you don't have to use this formula or anything like that. So I will show you how to use it on the calculator, because there is a nice calculator button for it. But if you are really into algebra and stuff like that and you want to solve these out by hand, feel free. I've kind of written the directions for you up here in blue. So just so you know, in case you've never seen the exclamation point before in a problem, so 4 exclamation point is actually read as 4 factorial. And so what it does is it starts with 4 and then just drops down by 1 each time and multiplies that number together. So 4 factorial is 4 times 3 times 2 times 1. 5 factorial would be 5 times 4 times 3 times 2 times 1. And then you'll see sometimes in problems we end up getting the 0 factorial. And so obviously you can't count down from there. So it's a given that 0 factorial is always equal to 1 in this case. And then that kind of makes things work out really, really nice. So, and then again, this is what the formula would look like if you wanted to do it by hand. And in a little bit, I'll show you how you could use it on the calculator also. But, all right. Oh, I guess, yeah, well, let me show you now. So, hold on, let me go to the calculator real quick. So, if we go to the calculator so I can show you. So, what we want to do is hit the math button. And then we want to hit the PRB, which is the probability button. And so what we're going to do is we're going to end up using 2, oops, I didn't mean to hit it right there, sorry. So math, prob. So we're going to end up using 2 and 3 eventually. And then if you ever want to use the factorial, it's actually number 4 in this case. Now, the thing you have to be careful of when you're using this formula is that usually you have to put in the first number first. So in this case, 4, and then we want to do permutation. So let's see some, whoops, oh my goodness, what did I hit? So math, so 4, math, probability, NPR. So the first number always tells us the total things that we're choosing. So in this case, the 4 is our 4 movies. And the second number is how many of those 4 movies we're actually choosing. So in the last example, we were only choosing 2 out of the 4. So we would hit 2 here, and then we would hit enter. And lo and behold, I ended up with the same answer that I had before, which is perfect. But you can also use it where, like in the first example, we had 4 movies and we actually chose all 4 movies. So you can do that too. So we could do 4, math, probability, NPR, and then 4, and hit enter. And lo and behold, we get 24 again. So you always are going to have the bigger number on the left. Like if your bigger number's on the right, you're going to get an error. So the left number is always the total. The right number is how many you're choosing. So the two numbers can be the same if the total and what you're choosing is exactly the same, but you're never going to be able to choose more than your total. So if you put in something like 4 math P5, that means it's an error. That means like some calculators gives you an error and stuff like that. So in this case, that's kind of what that means, because it's there's no way to choose 5 things if you only have 4 total to go with. But all right, so we'll come back to that in a second. So with that in mind, try practice 6, 7, 8, and 9 on your own. So again, these are all nice little permutation problems. Now you don't have to use the formula. Like even though I said use the formula, you don't have to use the formula. You can use the box method, like I like to call it up here. Or if you want to use the calculator and type it in using the calculator, that's fine. Like I don't actually want you to use the formula, even though I wrote that down there. Do not use the formula. What I meant is either use the box method or use the calculator. But all right, so do those 4, and then when you're done, come on back and we'll talk about combinations. All right. So hopefully everybody did a good job on permutations. Again, if you got stuck on any of them, please let me know so I can help you with them. And so now what we want to do is move into kind of what's called a combination. And so it sounds similar to a permutation, and they are in some ways, but there are subtle differences between them. So let's suppose we're working at a pizza parlor and we have a special on 3 topping pizzas. How many different 3 topping pizzas can you make if you have the following toppings and can't reuse any of the toppings? So notice this is one of the places where permutations and combinations are the same. So we're not allowed to reuse anything in a permutation or a combination. Fundamental counting, we can reuse stuff. Permutation, combination, can't reuse anything. And so in this case, we've got 4 different toppings to choose from, and we're trying to make 3 topping pizzas. So in this case, what I'm going to do is just sort of brute force try to list them out and see what we actually get. So this is kind of similar to when we were doing our sample space problems. So, and again, I'm going to kind of do that same thing I did before where I sort of hold one position fixed and then cycle through others. So I'm going to start off with ham, sausage, pepperoni. And so I'm going to leave ham and sausage the same and then throw in mushrooms. So now I'm going to leave ham the same, and I've already kind of used all the sausage, so I'm going to go through pepperoni and mushroom. And so that's all the ways to have ham first. And so now we want to move on to sausage, but in this case, we just get that one guy there. So in this case, based on our kind of brute force method, it looks like there's 1, 2, 3, 4 possible three topping pizzas that we can make. Oops. So some of you might be looking at my list going, well, heck, you forgot all kinds of stuff. I mean, because what about, you know, pepperoni, sausage, and ham. I mean, why isn't that on the list? Or why isn't mushroom, sausage, and ham on the list? I don't see that up there anywhere. And so, but if you think about it from a pizza perspective, does it really matter if you put the pepperoni first, then the sausage, then the ham, or if I put the ham first, then the sausage and the pepperoni? Ultimately, not really. And so that is the difference between a permutation and combination. So remember, permutation, you weren't allowed to reuse items, but the order mattered. Combinations, we still can't reuse items, but the order doesn't matter in this case. So what that means is there's going to be a lot less combinations than there are permutations, because these ones that are written down here would actually be included in a permutation list, but they end up being the exact same as these guys above because they're not ordered. So in this case, we don't need to double count them or anything like that. All right. And so I kind of gave this away in the green box anyway. So a combination is just, again, when they're selected from the same group of items, just like a permutation. No item is used more than once, just like a permutation. But the order of the items does not matter. So that's the big difference between a combination and a permutation. And I'm going to have some problems later where you have to kind of decide, well, is this a combination or is this a permutation or what? And so the big question you should always ask yourself is, does order matter? And so if order doesn't matter, it's a combination. If order matters, it's a permutation. All right. So, and here's our little formula for combination. So again, it's very similar to permutation. So if you actually look, the whole left-hand side is exactly the same. N factorial divided by parentheses n minus r factorial. The only thing that's different for the combination is that we're dividing out an extra r factorial in this case. Because the r, we need to, since there's a lot less combinations, that dividing by r factorial is taking rid of all those things that we would double count in this case. So again, your combination should always be a lot smaller than your permutation. So again, this formula is not necessarily the easiest, and you may not want to actually do it with it. And unfortunately, your only other way to do a combination other than the formula and the calculator is kind of brute force like I did here. And this was a small problem, so it was easy to kind of brute force write them all out. So you probably shouldn't want to do them that way because it could be pretty nasty. So I'll show you how to use the calculator. It's just like the permutation formula. So let me do an example so I can actually show you how to use the calculator real quick. So let's go back up to, which one did we have here? So this was, oops. So in our calculator, this would look like 4C3 because our total number of toppings was 4. And how many things we were choosing was 3 in this case. So let me go back to the calculator real quick. So again, we would do the 4 first. So you always put in the total number first, hit math, go to PRB. Now this time we want to use the NCR formula, and then we hit 3, and then enter, and lo and behold, we end up with the exact same answer. So again, just like a permutation, the number on the right should never be bigger than the number on the left. It could be the same number as the number on the left. Unfortunately, it's not very exciting if it's the same number. So you'll see here in a second. So if I do 4 math probability, it's always going to be 1. So typically you don't even see that scenario very often because again, if you think about it, if you're choosing 4 items from 4 items, well, since order doesn't matter, you're only going to have to write it down one way and you're going to capture everything. So it's very rare in a combination problem that the 2 numbers are going to be the same. Typically the 2 numbers should be different, otherwise it's not a very exciting problem to begin with. Permutations, the numbers can be the same and you'll still get a really big number, but not with a combination. So it can happen, but it's not very likely that it's going to happen because it's kind of a boring situation. But all right, so let's look back at our example here. So again, this one I've got kind of identify a permutation and a combination. So again, I'm going to read these out and then I'm going to think to myself, does the order matter that I actually put these guys in, and kind of go from there. So for the problem problems, identify where it's a permutation or combination. So how many ways can you select 6 free videos from a list of 100 videos? So in this case, like we're not talking about playing them in order. We're not talking about, we're just grabbing them off of a list and stuff like that. So does it really matter, if I grab 6 and someone else technically grabs the same 6 but wrote them down in a different order? Does it really matter? No, not really. So this one's going to be a combination. And in this case, our total number of videos is the 100. So to put it kind of in the form, we'd have 100C, and we're choosing 6, so we'd get 100C6. So I'll leave that for you guys to fill in using the calculator for practice. And then for B, we've got in a race with 50 runners and no ties, how many ways can the first 3 finishers come in? So in this case, there's a rank because we've got a first place winner, we've got a second place winner, and we've got a third place winner. So in this case, order matters. So this is going to be a permutation. And so again, since there's 50 runners, that means there were 50 possible people that could have come in first, 49 who could have come in second, and then 48 who could have come in third. Or if we were doing this using the P formula, we'd have 50 as our total P, and since we were choosing 3 winners, we would do 50P3. So again, I'll let you either practice that on the calculator or just multiply 50 times 49 times 48 just to see what the answer is. So finally, there's a bunch of practice ones for you guys to do. So 10, 11, 12, and 13 are all combinations, so you don't have to decide. You just use the C formula on the calculator to answer them. And then the next few here are all anything. So it could be a permutation, it could be a combination, it could be fundamental counting principle. So I'll leave those for you guys to try on your own. If you get stuck, definitely let me know. Otherwise, I'll be around the computer all day. So good luck and have a good time.